Recording. Okay, it's recording. We're only a couple minutes late. Okay, so nice to see everybody. Let's see. In terms of course announcements, it's a pretty easy one this time. You got a midterm. This is our next lecture slot. So the midterm will be here. It will start, like you will have the opportunity to open your exams and start writing things down at precisely 2:35. At 3:55, we will take your papers away. So if you're late, then you'll just have less time for your exam, so don't be late. We are not planning on, it's not a take-home thing, it is a thing here. You can have a sheet of notes, you can write on the back and the front of the sheet of notes, you can print it. You can use your favorite pen plotting device. You can bring a magnifying glass, whatever, a microscope, it's all good, whatever you want, you know. I would be shocked if you truly need that much surface area, but go for it. You know, you can print the entire textbook on microfiche and then glue it onto your sheet. That's fine. Yeah, so that's the way the exam works. Other than that, of course, it's closed book. The problems are completely uncalibrated because this is the first time we've taught this course. What that means is that if it turns out that it feels super hard, it's because it probably is. And don't worry about it, because obviously the grades in this class are going to be very high. Like really, it's not our job to give you a hard time. So like it's hard to calibrate these things. You know, obviously we will look at the distribution of scores and adjust upward. But if you're looking for good practice problems at this point from your homeworks and the problems in the back of all the chapters of the book, you should have a pretty good idea of the kind of problems that like your instructor tends to ask here. So hopefully you have a reasonable mental model of like the kind of things that we think are important. Chris and I just finished drafting the exam, and after class, if I manage to get like 20 seconds to rub together, we'll make sure that it's, well, like correct enough that Harry can tell us the errors within the first few minutes of the exam. Any questions about the logistics of that? Again, that is on Thursday. We're going to start probably at 2:35. I promise that I won't come dashing in late like I did today. Yeah. I think it's pretty straightforward as like exams go. The logistics, rather. The exam itself might be total hell. I don't know. It's hard to calibrate. Sorry, I'm giving you a hard time. But really, like again, you know, it's hard to calibrate these things. If it's really scary looking, just remember it's because it's probably we made a mistake rather than you guys. Okay, and the exam covers everything up to and including today's lecture, although you'll notice that today's lecture doesn't contain a whole lot of like testable content, and that's possibly by construction. Right, and then beyond that, your next deliverables are just a couple more homeworks and a final, and you're out of here. Easy. So today we are going to continue our discussion of optimization, and now we're going to kick it up a notch. In particular, we're going to kick it up from one variable to more than one variable. That's our job for today. So we're going to consider the following set of problems, which are optimizing a function f from Rn to R. We typically assume today that our function f is differentiable, or if you want to be mathy about it, differentiable almost anywhere, should do it for most of the stuff that we're doing today. Yeah, so that's the algorithms we're trying to construct. Now, obviously, remember we spent a big chunk of our previous lecture on a particular algorithm called golden section search, which is like a really elegant, cool way to do 1D problems. It is really not obvious how to extend that thing beyond more than, I would say 2 dimensions, like maybe in 2D there's like a clever way to cut up a rectangle that kind of looks similar, but so instead we're going to put a little bit stronger assumptions on the structure of our function f that allows us to make some progress. Namely, we're going to assume that f is differentiable, right? So what is the algorithm that we're probably going to cover today? What is the algorithm we all know and love as students in 2023 that have heard about neural networks since birth and do nothing but optimize and code in PyTorch? What will be the obvious optimization technique that we'll be covering for multivariable unconstrained optimization? Gradient descent. That's absolutely right. So, in particular, if you recall from our previous lecture, given a differentiable function f, we kind of justified that the gradient of f tells us the direction where we can like point our toes starting at x, where if we walk an infinitesimal amount away from x, f is going to, and you have to be careful, increase when I walk along the gradient. Because remember, gradient descent goes along minus the gradient. This is the #1 mistake that I see in student papers. Right, and in particular, if you look back at our proof from last time, you'll see that if I put a minus sign in front of everything, the rest of it still carries through, and we get the direction of steepest descent. Now, one thing to note is that is only a local fact, right? Like the second that I talk about displacing a positive amount away from x rather than infinitesimal, it could be that actually there's some direction that's slightly away from the gradient that does better, right? So this is really just a local fact about life. That's the elegant thing about calculus. In particular, if we want to word that a different way, here's a sort of a mathy way to phrase that sentence I just put down. The one thing that we know about the gradient is that it is what we would call a descent direction, is the phrase that you hear a lot in the optimization literature, which just means the following, that if I start at x, and I take a small multiple of the gradient, right, that's what's going on the left-hand side, then if alpha here is positive, then notice that, like, what is this? This is kind of like one step of gradient descent. That essentially for sufficiently small alpha, this thing should be less than or equal to f. Right? And like a Taylor series argument, it's enough to justify this fact. In fact, if you look at what we did in the previous lecture, it was basically that. But at the end of the day, that's sort of the very, very high-level intuition behind gradient descent. This is the reason we do it, is that at least locally, we have this little useful guarantee, which is we can make f a tiny, tiny bit better than it was by stepping along that direction. But notice that, like, at least in the Taylor series story that we know from calculus class, there are like a lot of missing pieces here. In particular, the word sufficiently is not very helpful for designing an algorithm, right? And so, like, I think when we talk about Taylor series, we talk about limits, which is fantastic. But at the end of the day, when we're actually writing optimization algorithm, we don't have such a luxury. We need to actually choose an alpha, and so there's still some engineering that needs to go into our algorithm. Does that make sense? So in any event, the algorithm that I think we all know and love for optimization, in fact, the one you probably were expecting like 3 lectures ago, looks something like this. So we iterate until convergence. Of course, that's also a bit of a squishy phrase, which is, so we start from a point xk, and maybe we can even define a one-dimensional function gk of t. So what is gk doing? So let's say that I have my function f, and maybe we're in 2 dimensions. Thank you for cleaning the board, by the way. I'm sorry, I'm a hot mess and was like running into the lecture at the last second. So let's say that my function has level sets that are like these, kidney bean shape? Does this look like a kidney bean? Sweet, maybe like a little guy. Okay. So if I do gradient descent, let's say that I'm starting here. This is a good example. So these are the level sets. So essentially, this is the minimum value is right at the center of the little kidney bean. And as I move farther out, right, I feel like we see these pictures a lot. Sometimes we forget what they mean. So what direction is the gradient point? Away. Away from what? Away from me? Away from the center. That's right. So the gradient point's uphill. Probably something like that. But in fact, we can say a tiny, tiny bit more, which is the gradient is always 90 degrees to the level set of the function. Yeah? This is a fantastic example where gradient descent is probably a really bad idea. Because what is gradient descent going to do? Remember, descent means I move along minus the gradient. So it's going to move somewhere along this line. Does that make sense? Now, the question is where to move along this line. If we wanted to find the most kind of generic version of gradient descent, maybe we do something like what's indicated on the screen here, which is to say, okay, so this whole function, you can think of this thing as f of x, right? So x here is in the plane, right? But so far, all we've talked about are one-dimensional optimization algorithms, right? So essentially, what we're proposing is to say, okay, I'm going to take like a little slice of this function here, and I'm going to view this as just a one-dimensional object. So notice that like for a little while, f decreases along this line until it reaches kind of that point, and then it starts increasing again. So I can kind of map that here into a one-dimensional function, which starts at t equals 0. We know that if I start at t equals 0, at least infinitesimally, I decrease, right? That's what we justified in the previous slide. For a little while, it goes down, and eventually at this magic point here, it starts going back up, right? And so essentially what happens in multidimensional optimization is I in some sense, reduced to a sequence of one-dimensional problems. Not everybody would agree with this description of gradient descent, but this is one way to think about it, where now I have the option of choosing any t along this line, right? I choose one. Maybe that corresponds to, like, I don't know, that point here. Did I? Yeah, that's correct. And now what do? I recompute the gradient. Maybe it's like, in this case, pretty similar to the one I started with. And I keep going, right? Now there's a trade-off, right? Which is I could work really, really, really hard, and I could optimize the bejesus out of this function gk, right? I could do, I don't know, Newton's method on that thing, which would involve computing the Hessian of f, probably not a smart idea. And like really work super hard to find this point here. And there's some argument to be said that this isn't a terrible idea, because then my next search direction kind of necessarily is going to be 90 degrees to the previous one. We'll come back to that when we talk about conjugate gradient. But I just lost a ton of computation, and did I actually reach the minimum of g? No, right? I've reached this point. I'm nowhere close to the center of my kidney bean. Yeah, I see Axel, but I'm gonna finish my story real quick. So it might have been just fine enough for me to like get my search a little bit off in that one-dimensional problem, but then start some new line search and just keep moving, right? So there's a trade-off here between how much time I spend optimizing G and how much time I spend optimizing the outer loop, right? Like optimizing F, right? And there's going to be no clear answer. I mean, on the one side, there's really dumb solutions, like choose a constant for T, right? And we're going to see for particularly nicely structured functions F, that's actually a totally reasonable choice. But there are other algorithms that actually put a lot of work into choosing that T really, really carefully. And these procedures have a name. This is called line search, which is, wow, that was supposed to be an A, which is exactly what it sounds like. It's a procedure for optimizing just along a line. But of course, they don't typically target a critical point. They're going to target something weaker. We're going to come back to that. All right, Axel, what's up? I'm worried. Fantastic. Good. My goal is to intimidate you guys into not asking questions. You know? Okay. So again, there's sort of an inner loop and an outer loop. The inner loop is trying to find a good t that decreases the function f. And the outer loop says, okay, now I'm going to recompute the gradient, right? And there's definitely a trade-off between these two things. So I think these days in machine learning systems, we see a lot of people that do the dumbest possible thing for the inner loop and then spend all their time on the outer loop. For other problems in engineering, where like maybe the function f is really, really complicated and computing its derivative is not so expensive, it might make sense to spend some more time in the inside. Make sense? Yeah. Yeah, oftentimes these procedures are iterative. That's absolutely right. So for example, a very simple strategy here would be the following. This is called backtracking line search, which is the following. Maybe I choose a t equal to 1. I just say, okay, I'm going to like hop along the gradient this far. I'm going to evaluate f at that new point. But what if f at the new point is actually bigger than f of xk? It could easily happen, right? I could jump over the min and then like climb back up. Well, then it might make sense to take t and divide it by 2, right? Do 1/2. And then if that one's still bigger, do 1/4, and keep dividing until I finally get something that's smaller than my initial point. And I know such a point exists, right? Because I know for sufficiently small t, my function will decrease. But I don't know what sufficiently is, so I could like just keep dividing t by 2 until I reach that point. That make sense? This is actually, I think, the standard strategy in most optimization software. It's pretty brain dead. Yeah. But there are smarter things you could do. For example, you could like try to approximate the second derivative right here and use some version of a Newton step at that point. This will work very poorly in machine learning systems where like it's hard enough to compute one derivative. But in other places, it's a totally reasonable strategy. Okay. And yes?
You say it's really hard to compute like the first or second derivative. Are you meaning that it is hard to like approximate it there if it's not given? Because I know some of these systems do, you can like hand choose the derivative, the second derivative, just kind of supply it and like, yeah, it's multiplication.
That's absolutely right. So if you use like SciPy, it has a library where you just give a function pointer to the gradient and the Hessian, and then all these algorithms are kind of wrapped around that. The other extreme would be in certain machine learning problems. So let's say, just as a short digression, and then we'll get back to our story here. No, it's fine. I'm like kind of alluding to a story, but not filling in the details, and that's goofy. So let's say that I have a bunch of data points, xi, yi, and I'm trying to find a function f theta so that f theta of xi is roughly yi, right? So I've got a lot of data points. The theta are maybe like the weights of a neural network, right? Then very typically, this is something called empirical risk minimization. If you want to be fancy at bar trivia, there's an R in there. EM is also an algorithm, but not this one. Okay, then I'm going to optimize the following function, which is, if you think about it, a function of theta, right? So this is typically in learning, maybe you call this loss. Apparently this spring I have to teach the giant learning class with like 5 million students, which I'm not looking forward to. Anyway, so you sum over your data set, and you say like, okay, I look at the output of my neural network at xi, I subtract off yi and I square, and maybe just for fun, I divide that by the size of my data set, because then it looks like an average. So it might be that like computing the gradient of f is not so hard, but notice that there's like an outer loop here. I have to sum over my whole data set, right? So a very typical thing to do, which is called stochastic gradient descent, the S here is the critical part. It says I'm going to subsample this sum randomly, because this is like the average of a big set of numbers. I'm just going to like average over a smaller set that's randomly drawn from the full thing, right? So if I do that, every time I do this, I get a different gradient, right? It's a noisy object. Turns out if I do that with a Hessian, it's even noisier. So like these kinds of algorithms, like the higher derivatives you get, the worse approximation there are. There's also some argument that like this strategy can kind of smooth out the gradients of your problem. This used to be mythology, and now there's some modern mathematical results that are filling in like the details. We probably won't get there in this class. Yeah, but this would be an example where like computing a gradient is expensive and noisy and hard. So for example, would doing line search during stochastic gradient descent make a whole lot of sense? Probably not, because that downhill direction is already unreliable, right? And when I do line search, I have to evaluate the function f, but that's already a random procedure. So I might like think that my function decreased a lot, but actually it didn't or something. So I think the standard in that community is to do one of two things, either to just choose a constant t, or to use what people call a learning rate schedule, which is just a sequence of t's that goes to 0, but like prescribed, not with any smart search procedure. Cool. Did I manage to TMI you the answer there? Okay, we like it. Fantastic. Okay, so in any event, we're obviously going to fill in a lot of details of this algorithm in many different cases. And that's our goal here. One thing I should note is that there is this little subtle line at the top here. We say iterate until convergence. We have to decide what that means. Any reasonable suggestions? How could I iterate until convergence? What would be reasonable criteria to see whether I stop? Harry knows because it was in his code. What was that? Yeah, that's a totally reasonable choice. This is sometimes called stalling. Where you look at like f xk and you compare it to f of xk minus 1. You say, well, if this difference is really small, then somehow my algorithm really isn't making progress and I'm just going to give up. For ill-conditioned problems, this is probably a tough criteria to use because of these like long, shallow landscapes of objective values. What would be a different one? Oh yeah, I mean, you could look at the relative error if you want to. Well, so, and by the way, a bit of exam review. We might call this some like kind of version of backward error. It's not quite backward error because neither of these is the minimizer, right? But if you wanted the sort of forward version of this, you might look at xk minus 1. So in other words, gradient descent isn't doing anything. Either of these are reasonable stopping criteria. If you play with like the MATLAB or SciPy optimization tool, you'll see there's like a billion different criteria you can choose from, and each one has a hard-coded constant. Yeah, there's no, no magic choice here. Okay, yeah, so like a reasonable, or yet another one would be, at the end of the day, we want the gradient to be what at an optimizer? 0. So what could I do? I could take its norm, right? Like I could say, okay, I'm not going to stop until the gradient of f is like pretty close to 0. Again, that squiggly equal sign is like it looks very mathematical, but the reality is this is where engineering happens, right? Like there's some hard-coded magic number that has to go in and say, well, my gradient is this small, I'm satisfied. I think we tend to choose 10 to the minus 8 because numbers. Yes, Chris. Yeah, good. See, I have the best grad students. They know. Yeah. Okay, fantastic. And one thing you might remember is that this is closely linked to the condition number of these kinds of problems. You should look back. Okay, so today we're going to briefly talk about some different line search strategies, and then we're going to talk about one case where line search is completely unnecessary. And so our goal is to get through one theoretical proposition today, which is the convergence proof for gradient descent in a really dumb case, which is where my line search is constant. In other words, I just always move times some multiple of the gradient that I stay fixed during the algorithm. We're going to show that that's actually not a bad choice, which is somehow very heartening. Do you see that? Because like what it means is even like the version 1.0 of our algorithm like already works okay. The rest of this is gravy, yeah? Under a lot of assumptions on F, of course. But really this line search procedure can have all kinds of interesting engineering. And again, it's this trade-off between getting a really good T here and essentially optimizing for the X's, right? I could do lots of iterations for T, or I could do relatively few and get a bad subsequent X, but then I have to reevaluate the gradient. So there's some trade-off there. Yeah? Now, the simplest thing we could do is just take any of our algorithms from the previous lecture and just stick them in this optimization for T, but that's probably overkill, right? So it turns out over the years, mathematicians have studied this problem, and what they want is that say like, okay, on the one hand, like optimizing until I literally find a critical point of this like one-dimensional slice is probably unnecessary because at the end of the day, it's not the thing I wanted anyway. On the other hand, what could happen if I do a really bad job of this? Do you guys have any ideas? Like, give me some like kind of boundary cases where line search is so bad that gradient descent fails.
You're doing like a fixed step size, and you're in some kind of like parabolic like bounce.
Yeah, that's a fantastic example. So let's say that I'm optimizing in one dimension, and I have a parabola like this. You could imagine a version of gradient descent where I take a step and it goes like over here, and then the next step goes back over there. Or like if I take my step even larger, notice that like an even worse thing happens, right? Like I start here and then it gets bigger and bigger, it actually diverges, right? That's absolutely right. Can we think of anything else that could go wrong, by the way? Let's say I say like, oh my God, like this is bad news. So I'm gonna take super small steps because I don't want this to happen. What was that? It'll take a long time for sure, right? Like if I take a little itty bitty, I tiptoe along that gradient, you can imagine a universe where like I need a million iterations. Can we think of actually a case where it's not just a question of computation time? Yeah. You could get stuck in local minimum. It turns out local versus global minimum here is not actually so obvious, right? Like at the end of the day, these algorithms are all targeting a minimum, but there's actually no sort of global reasoning happening here. Yes.
Could your step size be so small that the difference between subsequent iterations is numerically zero and you're literally making no progress?
Okay, we're getting there. We're getting closer, right? So like maybe I choose such a dumb step size, I literally make no progress. There's actually even a middle ground that's more subtle. Like maybe I have a really clever algorithm for line search, like it actually does adjust it, but like it's not that clever. Like it does something a little dumb, but you get a different T in each iteration. Let's say that my first T is equal to 1. Or I'm sorry, I've noticed, by the way, in the slides there's T's and there's alphas. Both of those are one-dimensional things. Hopefully we've caught on to that. Okay, but let's say that I take a step which is alpha equals 1. And then my next step is alpha equals 1/2. And then my next step is alpha equals 1/4. And then my next step is alpha equals 1/8. So every time I do that, my objective function does decrease ever so slightly. And in fact, my sequence of iterates, like this thing, it'll go to 0, right? Does that mean that I actually optimized my function? No, it just means that I chose a sequence of step sizes that got smaller and smaller and smaller, that when I add them all together, I get a finite number. Does that make sense? This is like Zeno's paradox, right? Was it Zeno's paradox? Is that right? I always confuse my Greek myths. Is that Greek? Okay. Cool. Yeah, that's right. So you have to, you're sort of balancing two things. You don't want to overshoot because then you can actually diverge. On the other hand, there actually is such thing as undershooting. It's not like one of these universes where if you're conservative, it'll just take a long time. There's a version of being conservative where you literally converge and you converge to something that isn't the optimum. You see that? And so it's actually a little subtle to get this right. Yeah. That's right. But if your step size is constant, you can end up in these like spiral out of control situations. Yeah. When you restart. Yeah, so if you have a line search procedure, then you can probably avoid this case pretty easily, right? Because you can detect if the function is increasing. It's a little trickier to avoid the case where you grind to a halt, right? Because you can imagine a line search procedure that's somehow so conservative that it just checks that you decreased. But like for whatever, like for instance, maybe I take the line search direction from the previous iteration and I just always divide it by 2 because I just felt like that was the right thing to do. And then that would be a bad policy, right? Because you would not converge to an optimum. Yeah. You could restart, but then you might end up exploding again. Yeah. Yeah, damn, this sucks. You're right. These are tricky problems. Yeah, so the high level point here is that you have to be so careful with this stuff. And I wish I could cover it in great detail, but it would take about 6 lectures to fill in every possible criterion. However, I do want to make you aware of a buzzword in numerical methods, which is one sufficient criterion to make sure that you make what they call sufficient progress. Right? It's easy to make sure that your line search doesn't spiral out of control. You just check the value of your function, make sure it doesn't get bigger. Right? That part's like kind of okay. The problem is like you could imagine a sequence of iterates that never converges or converges to the wrong point. Right? And those conditions, extremely famous, they are the Wolf conditions. How many of us have seen this? Like maybe if you called a piece of numerical code, it turns out like numerical software often checks these things behind the scenes and it'll like output these numbers and just say like, fun fact, like these are satisfied. So I think when you look at numerical analysis textbooks, they often just predict, like say, here's a criterion for a good choice of t's, that if your t's satisfy this, you're good. And it's totally not obvious why, if I give you these inequalities. But actually, if you start drawing pictures, you'll find that they're kind of reasonable. And so I thought today, rather than prove that theorem, we can spend like 10 minutes drawing a picture of what these two things mean. So you kind of get some intuition for like where they came from, at least. And then there's a very famous textbook, which I can point you to, that has proofs of 2 facts that together are what you need. One is, if D is a descent direction, there exists a T that satisfies these 2 criteria, right? Because you wouldn't want to be caught in a, you know, I'm doing gradient descent, and like, yeah, these are sufficient for convergence, but they're not actually satisfied by any step, right? And the second one is that if you have a sequence of such directions and such T's, that it really does converge to an optimum. We're not going to check that here. This is just so you guys are thinking about the kind of stuff that people in this domain have to do. Right? Okay, so let's draw pictures of what this stuff means. Incidentally, I'm lifting this little chunk of our discussion from a very famous textbook in this space. Sorry, I'm looking for the eraser. That's okay. I thank you for cleaning the board. There's a really fantastic textbook out there. I'm a big fan, which is Nostal and Wright. Wright is a really nice guy. I've never met Nostal. Okay, and it is like the nonlinear optimization textbook. It has like a little butterfly on the cover. It's very cute, and it goes through this stuff in great detail and is relatively approachable. I have my quibbles with their notation, but the content's nice. And if you buy the Chinese edition, it's very cheap. Okay, but in any event, what was that? It is in English. It's just printed on like tissue paper. Okay, so in any event, I thought I would spend a minute illustrating these 2 conditions to kind of see like why Wolf apparently kind of came up with this stuff. And they look something like this. So let's talk about, I assume it's Armijo rule first. So remember that all of these things have to do with line search, so it's kind of enough to draw one-dimensional functions. It's just a question of like sort of making sure we interpret all the quantities that are in this expression. So let's start with the first guy, Armijo. I really should have looked it up. I assume it's Armijo. Somebody can check Wikipedia. Okay, and again, just to copy it on the board, this is f of xk minus t k dk. So here d is the search direction. So far this is is the, you know, all right, sorry, I put a plus here. This is the gradient, or minus the gradient. And what do we want? This is less than or equal to f of xk plus c1 tk dk transpose. Sorry, c1. T K dk transpose grad fk. Okay. So this thing looks like a hot mess. This just looks like a bunch of symbols. But let's see if we can break down what's going on here. Okay, so first let's look at the left-hand side. So remember what we're doing in line search. We're choosing a positive t, we're starting at x, and we're moving along a positive t multiple of our search direction, right? So what is the left-hand side of this inequality? Let's think critically for a second. So like, again, oh no, I erased our kidney beans, but like remember we drew that line? Yeah, this is just the next iteration. This is just xk plus 1, right? So the left-hand side is saying, okay, I'm just going to evaluate f at the next point, right? And what do I want? Well, if I didn't have this second term here, by the way, C1 is typically a very small positive number. It's like between 0 and 1 conservatively. According to Nostal and Wright, the proper choice of C1 is 10 to the minus 4. Fun fact. That's total mythology, but I was entertained by the fact that there's a footnote saying, like, this is the number we often use. In any event, notice if this term weren't here, what is this condition saying? Yeah, it's saying if I'm trying to minimize f, at the very least, I better decrease my function a little bit, right? But then what we want is for it to decrease, but like decrease in a way that's sufficient. So in other words, so sometimes, by the way, this thing is called sufficient decrease criteria. So let's like take a look at the right-hand side a little more closely. So what is this thing? So ignoring the C1, notice that this is extrapolating the value of f along the d direction for t time. Right? So this is the linearization of f evaluated at t. And what it's saying is that I'm going to allow there to be a little wiggle room. So it's saying this is the predicted decrease, right? So this is like the value that the linearization of, if this term weren't here, that the linearization would predict the value is at this location, right? And I'm going to multiply it by some small number. So I'm going to say, like, it's okay if I don't quite decrease as much as I wanted to, but I do want to decrease somewhere that like looks linear in where I started. So if we draw a picture here, let's see if I can manage to draw this. So we have, as I've proven in this class many times over, I'm terrible at drawing these things. Okay, so let's say here's our one-dimensional slice. We are in the non-convex optimization space, so we need at least 2 bumps. So if we look at this thing as a function of tk, is c1 is equal to 1, right? Then that's just the linearization. That's just this, right? So like in an ideal universe, it would be fantastic if the value of f were really that straight line. But sadly for us, it's not. It curled up, right? So what do we want to double check? We're going to say, okay, I'm going to take the slope of that line and multiply it by a small constant. So I'm going to allow this line to actually maybe have a slope like that. And now, let's see if we can find all the different points. Right, so now if I kind of draw this curve like this, what I'm saying is that I would like to be somewhere in these regions where I do at least as well as the linearized version of my function if I like kind of kick this slope up a little bit. Okay? So in other words, like in this region here, notice that the value of f is worse than the linearization would predict. Right? Where here, I'm giving some wiggle room to my linearization. I'm not just using the Taylor series. I'm actually letting the slope be a little bit better. So the reason that we want to use this criterion is that it's sort of saying, like, I would like something that kind of looks linear in my search direction size. Like if it's like somehow just like an exponentially tiny decrease of f, then like I haven't really made enough progress. And I know that for small enough t, I can get that linear thing. That's what Taylor series says, right? So this is really a condition for preventing t's that are like way too big. Cool? Good, okay. So that's rule number 1. This is the sufficient decrease condition. And I think this is probably the right phrase, right? It's saying that like if it decreases but not very much, that's not so good, yeah? Okay, the second condition is curvature condition. Let's see if I can manage to draw this. Oh man, okay. Right, so the way to, so the way to think about this is you want to take steps that aren't too big. We'd also like to make sure we don't take steps that are too small, okay? So let's draw what that might look like. Okay, so in particular, now we have this other condition. I'm going to get rid of the minus signs on both sides, so we can say this is dk transpose grad f of xk plus tk. dk is greater than or equal to c2, which is another small positive number. dk transpose grad f xk. Also looks like a bunch of symbols, but I claim that it's actually, again, not so bad. So what is this thing? Well, this actually has a name. This is the directional derivative of f evaluated at the next iterate. Right? Remember how directional derivatives work? It's like the dot product between the gradient and the direction. Right? So this is saying that if I displace from this point a tiny bit in the dk direction, this is like how much it'll change. Cool? And what is the right-hand side? Well, again, if you ignore C2, this quantity here is the directional derivative at the previous iterate. Okay, so let's draw a picture of what this curvature condition is saying. Okay, so now we've got curvature here. Curvature. Okay. This is even harder to draw. Okay, so let's say that my function does that. I'm trying to choose a function that like satisfies that where the condition isn't satisfied just for like stupid reasons. That's what's happening here. Okay. So let's say that I compute the slope of this thing, which is like that, right? Okay. So notice, so this thing is a constant and it's less than 1, right? So let's look at all the other points that also have the same slope. So that, in other words, I take this little parallel line and I just kind of translate it. I get something there. I get a point here-ish. I get a point kind of here-ish. And that's all. Okay? So this is saying, well, it's saying that if I decrease faster than this thing, then my point is no good. So in particular, like if let's draw dotted lines. And this feels counterintuitive, but it makes some sense. So in particular, the regions where it is okay for my algorithm to stop are like here. And why is that? The sort of intuition is that like if I stopped here, right, so my curvature is kind of facing downward there, then I clearly could have made more progress by just going farther. Right? And so that's what this condition is sort of expressing. That like if my slope is changing in some global fashion in a way that's like falling downhill, then I should choose a bigger search direction than I did. Yeah. It is like the second derivative. It is notice, it is precisely the second derivative. It is the change in the first derivative between these 2 points. So it's like some global version of second derivative. That's why they call it the curvature condition. That's a great intuition. Yes, Paul. Right, so far in gradient descent, dk is minus grad fk.
Right.
Yeah.
Is that the case why it's basically the norm?
Let's see here. Yeah, because that's the rate of change of derivative if you move in gradient descent direction. Yeah. Remember, like yesterday when last class, we justified the direction of the gradient as the steepest descent, and the amount of steepest descent was grad f squared. That is precisely what you're seeing here. Yeah. So again, these 2 conditions together are essentially saying we're not too conservative, and we're also not too liberal, right? So like the Armijo condition is sort of saying that like I don't want to go too far. On the other hand, this guy is making sure that I don't like grind to 0. Yeah. And so it turns out this is not something we're going to prove in this class, although it's like well within the skill set that you guys have. It's just lengthy. That essentially these 2 things are sufficient for reaching a critical point of f under some nice assumptions on f. By the way, like these look very abstract because they are. I mean, hopefully these pictures help kind of illustrate the spiritual argument here. One thing that you might kind of ask is like, okay, how do I translate this to an algorithm? Like what does this look like in code? And notice that it's actually totally implementable, right? So the user supplies constants C1 and C2. Again, according to Nussbaum and Wright, it's 10 to the minus 6 and 10 to the minus 4, but that's BS. And now I do my line search procedure, right? So I try different t's. And notice that everything in these inequalities can be just checked. I can just check these numbers and see if the inequalities are satisfied, right? So a very common backtracking line search procedure would be to just like keep taking t, and like maybe if it doesn't satisfy the curvature condition, then I multiply it by 2. If it doesn't satisfy our Miho rule, then I divide it by 2. Like you can imagine some kind of binary search that figures out a point that's satisfied by these things. The only thing you need to convince yourself is that such a t exists, and I'll defer to that textbook for that argument. Make sense? It's a complicated story because it is. It's really hard to make sure that these optimization algorithms actually converge to a critical point. Like my basic point, the high-level takeaway you should get from this lecture is these are hard things. And I think we often don't think about it carefully, especially these days because we all implement gradient descent. And for a lot of machine learning objectives, that's perfectly fine. But for other problems in engineering, computer graphics, it really isn't. And actually making sure that you find a critical point is a really tricky balancing act. Yes?
An example is like a characteristic of a problem.
Characters of a problem where this would fall apart. Well, they can't as long as you're differentiable.
Gradient descent.
Right, so gradient descent with like a constant step size, like if your slope is varying a lot as your objective function changes, that's the kind of problem where like this kind of procedure is needed. Yeah. Okay. So these kinds of line search procedures are really nice. If you download like industry grade optimization software, like what's, Mosaic, Garobi, what are some of the non-convex ones? Nitro. There's all like a whole software ecosystem out there that they sell to mostly engineers that want to use this kind of stuff, and finance people that like would like the last couple digits because of the dollars. That's really fantastic. On the other hand, notice that you spend a lot of time just choosing a t, and you're still not done because the outer loop over x. This is like one step of that. On the other extreme are the really brain dead algorithms that say, okay, I'm not going to optimize for t at all. Instead, I'm just going to like choose a formula for t as a function of k, right? Now, the simplest one would be tk equals constant. We're actually justify that that's an okay thing to do. That's going to be our sort of last task for today's lecture if we get to it, but I'm talking too much. More generically, you can imagine that this is actually sort of a reasonable heuristic for choosing a sequence of t's, which is you'd like them to go to 0 in the sense that like, if you're always taking a positive step on the gradient, you could imagine just kind of like wiggling around the optimal point forever. On the other hand, you don't want to end up in this Zeno's paradox situation, so maybe you choose the sequence of t's that sums to infinity, but the individual t's go to 0. Can anybody give me an example of a function tk that would satisfy that? Harmonic series. That's right. So like if I chose tk equals 1 over k, notice that the step sizes 1 by 1 go to 0, but that's not going to prevent me from getting somewhere because these do sum to infinity. It just could take a long time. Sneaky, huh? Yeah. These people are so clever. Right? This is like such a fun little area of math. Like people really think about all the little corners and problems because it turns out if you don't, you write your code, it just poops out. It's frustrating. I built a whole career in this space. It's bad news. Don't recommend it. Okay, so right, so there's a lot of different names for this kind of strategy, and there's all kinds of mythology about that these days in optimization. So oftentimes, by the way, I'm calling t a step size. In learning, they call that a learning rate. But I don't like that terminology. I think it's spiritual sounding, so we're going to go with step size in this class. And then oftentimes what they'll call this function of k as a learning rate schedule, right? And there's all kinds of interesting heuristics out there. The book actually talks about a few of them. Like for instance, like there are actually tools out there. I think you can add them to your favorite PyTorch code, where it's like a function of k, and maybe you like, so like here's the 1 over k learning rate function. There's actually people that use all kinds of crazy stuff like cosine, which is just wild. I guess the sort of high-level reasoning here is that this is it's like an explore-exploit kind of thing. Like my step size gets smaller, so I decrease my objective, and then every once in a while I just take a giant step and maybe I hop out of that well in my energy function. There's very little math in this domain, but there's a lot of empirical stuff. Yes, Chris?
There's actually a paper that came out like a couple of months ago that I saw someone post on
Yeah.
Twitter from some ML optimization person that shows that kind of strategy where you periodically take a huge step
Right.
is provably better than standard, decreasing step size.
Right. Right, so as long as you define better to be the set of functions for which this algorithm works well, this thing works better relative to the alternatives. No, this doesn't surprise me. I mean, like, you could imagine a situation where this 1 over k thing is sort of too conservative, and like it ends up in like sort of the closest well of your energy. Whereas like maybe this strategy, you do want to invest some computation in getting close to the minimizer before you take a big jump, which is kind of what's going on spiritually. I'm sure there's better theory out there, but Chris can share that on the piazza if you want. Yeah.
Why does the sum have to be
Because remember, we don't want the Zeno paradox situation. So the very simplest example, it's non-differentiable, but let's not worry about that for now. Let's think about f of x is equal to the absolute value of x, okay? So then my function looks like this. Okay. So then, of course, f prime of x is equal to x over absolute value of x. So basically, it's equal to +1 and -1, right? So let's say that my step size here, k, is equal to, I don't know, step size tk is equal to 2 to the minus k. And I start at 7, right? So then xk will be 7 minus the sum 2 to the minus k, which will converge to, I always get it wrong, 5 or 6. Depends on where k starts, I guess. But it won't converge to 0, which is what you want. Yeah. Isn't that annoying? Like, these are really subtle. Yeah. Whereas what will happen if you take t to be 1 over k, it still sums to infinity, but like what will happen is like you'll kind of like do one of these. Yeah. In fact, let's prove that. Thank you, Paul, for that brilliant and useful question. So, in particular, we might ask the extreme question, which is, what if we do the dumbest possible thing? We just take tk to be a constant. Can that algorithm ever work? Notice for absolute value that it actually doesn't, right? Because like I'll get, like, let's say that here's my function. For a little while, maybe I spiral in, but now, like, essentially I'm always setting a constant in that case, so eventually I'll just kind of get stuck here, right? I claim the following kind of fun fact, which is actually, I think, roughly why a lot of these machine learning tools work, which is that if I add a tiny bit of curvature to my function, this cannot happen. Okay, so let's prove that. In particular, what we're going to do for the rest of today's lecture is prove this useful proposition, which seems really lengthy, but actually is not so bad. and the reason that we're going to do that is because you need it on your homework. Oh no, I gave that away. Yeah, then Axel makes it. Okay, so, right. You might notice there's a problem in your homework that asks you to justify that like a gradient descent procedure converges. And we kind of only have one theoretical result that justifies such a thing. So, right. Here's what this says. Let's say that I have a function f, and now we're going to think of it as convex and twice differentiable. So remember what convex means. This is bowl-shaped, right? And now we're going to put one additional constant, or one more constraint on f, which is that it's Lipschitz, meaning that essentially differences in its gradient are upper bounded by distances, right? So in other words, I can't have two really close by points that have really different gradients, right? Like that's one way to read that condition. Yeah.
To go back to what we were talking about before, that stops.
Right, so exactly. We're going to kill that wiggly thing. We're going to have a nice bowl-shaped thing, and we're not going to have, in particular, like absolute value does not satisfy this because right around this point, the gradient changes infinitely quickly. Yeah. In fact, I think you can cook up smooth functions where this is the case. Okay. So, yeah, you clearly can. Right. So, let's take x star to be the minimizer. Then what we're going to show is that gradient descent unconditionally converges with a constant step size, so long as you choose it below the 1 over L, where L is the Lipschitz constant. In fact, it converges at a kind of linear rate. This is exciting, right? It means that as long as we have a nice bowl-shaped thing, which turns out to be most problems in the universe that we care about, you can ignore everything we've done in this lecture and just kind of guess a small step size, and you're probably okay, right? Okay, so let's prove this fact. Fun fact, if you downloaded the textbook before yesterday, the proof was completely wrong. But as of this morning, it is correct. That's my bad. The problem is that like sometimes I want to prove these things myself without spying on someone else's book, but you know, I'm bad at math, so those two things don't go together well. But this version must be correct. You know, by that I mean I introduced a bunch of simplifications to Ryan Tibciarani's notes, which is like probably a mistake because he's a big deal, that one. Okay, so we're going to prove a little lemma first, and then we're going to prove this result. That's our goal for the rest of the lecture today, right? Okay, so here's going to be our lemma here. So let's take any x and y. By the way, everything we're going to do is under the assumptions for our theorem here. Then essentially we're going to bound, we're going to say the following, that f of y is less than or equal to f of x plus gradient f at x dot product y minus x plus 1/2 L y minus x squared. Okay, so what is this theorem saying? So if I didn't have this third term here, notice that this is just the linearization of f, right? So if we want to draw a little picture of it, here's f. Remember, f is nice and smooth and bowl-shaped. Nothing too crazy can happen. Right? So the first two terms are just like this straight line. It's a straight line. It doesn't look like it on the board, but it is. Okay? So this much is certainly true just by convexity. I don't need a fancy lemma for this. But I'm going to claim something slightly stronger, is that I can stick like a little bowl on top of this thing. And as long as the coefficient in front of that bowl is really small, so clearly here, this picture that I didn't do it right, I can still upper bound f of y by this bowl here. Actually, I did do it right. I'm sorry. This bowl, yeah, something like that. So now I've kind of bracketed my function. On the one hand, I know f of, so like this is y and this is x, right? Then we know that f of y is bigger than the linearization. That's convexity. Now we're showing that it's smaller than this bullshit thing. Cool? Okay. I'm going to erase this picture before you find a flaw in it. Okay. So this is a simple calculus argument. At least I think it is. The fancy notes that I was borrowing from use like weird things about eigenvalues of Hessians, but I don't think it's necessary, and you're going to tell me where I made my mistake. That's how we're going to brand this little exercise. So let's define a function, phi of t, which we're going to call f of x plus t times y minus x. So this is kind of like doing line search from x toward y. Cool? So let's say we remember the fundamental theorem of calculus. Remember what this one says? It says that like integrals and derivatives cancel out. So in particular, I can write a very fancy formula. Phi of 1 is equal to phi of 0 plus the integral from 0 to 1 of phi prime of s ds. I don't think I've said anything too controversial. Okay, so let's expand this expression. What is phi of 1? I just defined phi for you here. F of y, that's right, thanks, Bob. What's phi of 0? F of x, thank you. Plus the integral from 0 to 1. And what is phi prime? Well, if you think about it, it's the gradient of f evaluated at x plus t times y minus x d, or I guess s here, sorry. Dot product with the derivative of this thing with respect to s. So that's just a y minus x ds. Have I gotten it wrong yet? I think we're good. Okay. So remember our goal here. We're trying to upper bound f of y. And we have a dot product here. And there's kind of like only one inequality that we know how to use. What is that inequality? How do we upper bound dot products of things? I've asked literally this precise question in lecture before. Yes? Cauchy-Schwarz inequality. That's absolutely right. So in particular, this is less than or equal to f of x plus the integral from 0 to 1 of the norm of the gradient of f of x plus s times y minus x, 2 norm times y minus x, 2 norm ds. Cool? Chris looks suspicious. You're making me nervous. He's very furrowed. I'm very sensitive to that. Okay, but notice, now we're cooking with gas because we have something that kind of looks like this. But unfortunately, this one's squared and this one's not squared, so we're not quite there yet. So I'm going to do something very profound, which is I'm going to add and subtract the same thing, which is this middle term. Okay? So I'm going to add it because I know that that should be there. So in particular, this is equal to f of x plus the gradient of f at x dot product with y minus x. But now I have to subtract that, right? But I'm going to subtract it by, oh no, wait, oh man, I already got this backward. I'm sorry. I'm going to do a bad thing. You're going to be really angry at me. I'm so sorry. I got so excited that I skipped a step. Okay? I'm so sorry. We're going to skip this previous inequality. It's correct, but it's not the inequality we need. Okay. But a very similar inequality we're going to use in just a moment. So let's say we're going from this one to this one. I'm going to insert this term, and then I'm going to apply Cauchy-Schwarz. That was the mistake I made. Okay? And notice that I have the dot product between grad f and y minus x. And I also have a dot product between grad f and y minus x. So this is plus the integral from 0 to 1 of, I really want to apply Cauchy-Schwarz, and I'm skipping steps. I'm sorry. Grad f at x plus s times y minus x minus grad f at x dot product y minus x ds. Okay, my apologies. So how did I get from here to here? Let me repeat myself because I made a mistake, and I'm sorry, your instructor is only, we're human, it happens. Okay, so essentially I wanted a bound that looks like this, right? And so I'm kind of reverse engineering that bound. And so the way that I did it is I just stuck this in, but then I have to subtract it. But of course, this is equal to 1 times this thing, right? So this is the same as just subtracting it there, because this is really just a constant in that integral. Okay, now we're good. Does everybody trust me? Okay, so let's look at just the second term. So this would be the integral from 0 to 1 of grad f dot product with this thing. But there's no s dependence, right? So this is really just 1 times that. Yeah. Okay. I'm sorry, guys. It happens. It's my bad. Okay, so now we're in better shape, because notice the first 2 terms here agree with the thing we're trying to prove. And the third one, well, it doesn't quite have what we want to prove, but there's a dot product, so we feel like there's Cauchy-Schwarz. And moreover, the only thing we know about f is that it's Lipschitz. And notice that there's a difference between gradients. It's almost like I knew that. Okay, so let's actually apply Cauchy-Schwarz now. I'm getting all hot and bothered because I got it wrong. I worked so hard on this morning. Okay, so we're going to upper bound this integral. In particular, this thing is less than or equal to f of x plus gradient of f at x dot product with y minus x plus the integral from 0 to 1. And remember how Cauchy-Schwarz works. It's just the norms of the 2 guys. So this is the norm of gradient of f evaluated at x plus s y minus x minus the gradient of f evaluated at x 2 norm times the 2 norm y minus x ds. Paul looks suspicious. We're good. Notice that this is exactly the same as the previous one. All I did was take what was dot producted and turn it into a product of 2 norms. Whew. But now we're doing pretty good, because this is a constant. Cool? Okay, so first of all, I can move that constant out here. So really, it's just the integral of this first guy, right? By the way, the reason that I use this proof instead of the one I found in the notes is very similar to what people do in differential geometry for like computing geodesics. But in any event, what am I to do with this first term? I mean, I told you like 2 minutes ago. What should I do with this first term? Harry looks smug, but he still won't answer my question. Yeah, it's Lipschitz. I can apply the Lipschitz property. It's the only thing I don't know yet, right? Remember from the statement of my theorem, I have this fact, that if I have differences in the gradient of f, then that is upper bounded by L times the distance between those 2 points. So let's apply that over here. Okay, so this is less than or equal to f of x plus gradient of f at x transpose y minus x plus, let's pull this guy out like that. And then we have the integral from 0 to 1. And this is less than or equal to L times the difference between the things on the inside, which is the norm of s times y minus x. Cool? Now what do I do? I'm dying. Help me, please. Well, so let's think. The one thing we don't like is this integral. Yeah? Notice s is a positive number, so I can just move it outside of this norm. Yeah? So let me write this in a more obvious fashion. You guys are really making me work today. So this is f of x plus gradient of f x dot product y minus x plus norm of y minus x squared, maybe stick an L over here, times the integral of s ds from 0 to 1. Does that make it more obvious? Thank you. And this is just 1/2. Exercise left to the reader. Cool? And notice that was exactly what we wanted to prove in our little lemma here. Any questions about our little curvature thing? So that's why this sort of strict notion of convexity is useful here, because it allows us to bracket values of f from below and above. Yeah. Whew. Okay. So we've got 15 minutes to show that gradient descent converges on this damn thing. Okay? So in particular, we are going to choose, if we look at the statement of our theorem, a step size t which is constant and less than 1 over L, which kind of makes sense. It's like somehow we're going to end up canceling this guy here, right? That's clearly where we're aiming with this. And we're going to show that for bowl-shaped stuff, if we do gradient descent, we can do it with a constant step size and it will converge to the optimal point. Cool? This is exciting. I mean, this is cool. Like, this is a dumb algorithm where we're showing that it works. I don't know. I think it's neat. Okay. By the way, when we talk about the conjugate gradient algorithm, we're going to prove a stronger version of the same result, now that I think about it. Okay, so now this page of notes goes away. This was the textbook before I fixed all of the bugs in the proof that was in the version that you have. But I digress. This little lemma makes it a lot cleaner. Okay. Great. Are we okay with my erasing this board here? Like the inequality is still stated at the top of the previous board. I just need some space. Okay. And again, this is all in the book. I even had one of my postdocs double check my proof because I don't trust myself. He did find several bugs, but I fixed those too. So now we're good. Okay. What was that?
Postdoc approved.
Yeah. No, he gets this funding for the semester. Okay, so here's going to be our trick. Okay, so we're going to choose y to be a very particular value. We're going to say y is equal to x minus t times grad f. So in other words, like we're going to see like what happens if I do a step of gradient descent with this carefully chosen t, because again, our goal is to show that f decreases a sufficient amount, right? Like that's what we're after. Okay? So in that case, what is f of y? Well, by our inequality, this is less than or equal to f of x. And now we have to plug in our annoying expression here, right? So this is equal to grad f of x dot product with y minus x. But notice that y minus x here is minus t grad f at x, like that, right? I'm just taking our inequality here and translating it into that case, right? And then we have plus 1/2 times L times y minus x squared. Again, that's going to be t squared mod grad f of x squared. Cool? So here, all I did was plug in this choice of y into the inequality we just proved. Cool? Okay. All right. So in particular, if I clean up this middle expression a little bit, this is f of x plus, minus t grad f squared. Notice that it's f dot product with itself plus 1/2 lt squared mod grad f squared. That's kind of nice. I can group together like terms here. Yep. This is clearly equal to f of x minus t times, we've got a 1 here, minus, I guess, 1/2 lt grad f squared. Okay, so I just grouped together stuff. Cool? And now, remember, what do we know? We only know one thing about L, is that we chose t to be less than or equal to 1 over L, like that, right? So in particular, this thing is going to be less than or equal to f of x minus t over 2 times mod grad f of x squared, just by plugging that in here. Okay. Whew. So, by the way, notice, this is already a good thing. This is not true for gradient descent, generically speaking. What did we show? We showed if we took a gradient descent step of length t along our gradient, our objective function decreases by at least this much, right? Because this is a positive number. That's good. So at the very least, we know that the iterates decrease f, but we don't know that it goes to the minimum. Make sense? Okay. So what are we going to do? More inequalities. That's what we're going to do. Lots of inequalities. Okay. So that's the last time we're going to need our proposition here, which just to like prove this little fun fact. So now I'm going to erase it. Ugh. Okay. So now let's apply convexity of f. So in particular, if we think about convex functions, let's draw our little picture again, and we linearize at some point. Notice that we have to sit above the linearization, right? So in particular, we can say the following, that f of x star, where x star is going to be our optimal point, so that would be like here, right, is greater than or equal to the linearization. So this is going to be greater than or equal to f of x plus gradient of f at x transpose x star minus x. Okay? Cool. So let's rearrange this ever so slightly. We're going to move this guy here. So f of x is going to be less than or equal to, like we're just going to subtract this from both sides, f x star minus grad f of x dot product x star minus x. Okay, at least this step I think is pretty clear. Okay. So now what we're going to do is continue our chain of inequalities that we started up here. Okay? So in particular now, we're going to, if we plug in this expression, right? So you notice that I've upper bounded this first term here, like that. Well, what have we shown? what we've shown is the following. That f of y, we're going to go ahead and subtract off this term from both sides. So minus f of x star is less than or equal to gradient of f evaluated at x times x minus x star. Right, so that's this term here. I swapped the ordering. Okay, and then we still have a minus t over 2 mod grad f squared. That makes sense? So I took this previous inequality and I substituted in this thing, and I just moved the x star to the left side. Notice now we're doing pretty good because we're starting to kind of figure out our relationship to the optimal value of f, which is what we're after, right? Okay. So now we're going to do some more algebra because of course we are. These things are gross and like this is a nasty proof. Okay. So in particular, where are we? Okay. So this thing is equal to 1 over 2 times t times this whole expression multiplied by 2t. So this is 2t grad f of x dot product x minus x star. And now we've kind of factored out the t, except it's the wrong kind of factor. So we're going to get minus t squared grad f x squared. Okay, so all I did was just pre-multiply by 1 over 2t and make sure it distributes correctly. Okay, so what we can do is add into the sum and subtract the same thing. So in particular, we're going to subtract x minus x star squared, and then we're going to add it again. Like that. We can certainly do that in these parentheses. We can add, this is just a complicated way of adding 0. Now, I'm looking at the clock, and we have 5 minutes left, so I'm going to skip one step, and you should all copy down on your notes, and you should check it at home, because I make a lot of mistakes, and this is where it's going to happen, is because I'm going to make a sleight of hand. Okay? Which is the following. We're going to leave this guy here, okay? And we're going to, if you expand out all of these products, you can refactor it. This is what I'm going to ask you to believe me, just because it's a lot of writing and not a very exciting little bit of math. But if you just do a bunch of algebra on this expression, what you're going to arrive at is the following. This is equal to 1 over 2t times, we'll keep this term here, so it's x minus x star squared. And then a really clean thing happens, that this ends up being minus x minus t grad f x minus x star squared. Yep. You can kind of see what this is going to happen. Notice that like there's a t squared here, and that's like coming from the expanded square there. Like it's not totally surprising that you can factor this way, but there are 3 terms, and this is kind of nasty. Is everybody okay? I can write it out. We do have 3 minutes. You're so quiet. See, the problem is I skip one step, and then you guys all tune it out, and you refuse to engage. Really, it kills me. Okay, but in any event, these 2 things are equal, and it's really just a question of expanding a square. Okay. Notice. What is this thing? This, well, let's call this y. Okay. Or, oops. Oh, not this way. Sorry, I grouped the wrong one. This is y, right? Because this is our gradient step. So really, this entire expression is quite clean. That's a really beautiful thing that happens. This is equal to 1 over 2t times the distance from x to x star squared minus the distance from x star to y squared, like that. Okay? All right. So now we're almost done, I promise. So if we read back through our chain of inequalities, notice what we've bounded so far. We've said that we take one step of gradient descent to get to y, and we look at the difference between f of y and f at the optimal point, and we have upper bounded that now by an interesting quantity. There's 1 over 2t times the distance from our previous the optimum minus the distance from the next iterate to the optimum. This is very geometric in nature. Okay. So now we're going to start getting a little sneaky, in case we weren't already. So in particular, remember what we're aiming to show is this inequality here, right? Like we're trying to show that like eventually our thing converges, right? That's what we're after. Okay. So let's apply this inequality more than one time. In particular, we're going to sum from I equals 1 to k of f of xi minus f of x star. So it's sort of like the error in iteration 1 plus the error in iteration 2 plus the error and so on, all summed up together. This seems like a weird quantity, but we're going to use it in a minute. Okay? Well, by our inequality, this thing is upper bounded by 1 over 2t times kind of a really interesting thing, because notice that this is the difference between two subsequent iterates. So we're going to have a nice telescoping thing that happens. So this is the sum from maybe I equals 0 to k of oops, there's a slight typo in the notes. Xi minus x star squared minus xi plus 1 minus x star squared. Do you see that? Because again, remember how I got y from x is by taking one step of gradient descent. So notice a really clean thing happened, right? Because this is the sum from 0 to k. This is like the sum. So so this should go to k minus 1, I guess. This is like the solution, the sum from 1 to k, and they're both actually the same terms. There's actually one thing left after taking this difference, right? So in particular, this is equal to 1 over 2t times x0 minus x star squared minus xk minus x star squared. Every other term here disappears because it's like the first term minus the second minus the third, and so on. Okay? And if we regroup this thing a tiny, tiny bit, oops. In particular, this is a negative number. So this is upper bounded by x0 minus x star squared over 2t. Okay? So this is kind of interesting. Notice what this is saying. Does this have any k dependence at all? So like kind of a funny thing happens, which is I can add up all the increments of my errors, and then they're always upper bounded by this value here. What was that? So this thing is a function of k, right? Yeah, I can keep adding terms, and kind of shockingly, it's upper bounded. This is not at all obvious. Yeah. So now we're going to do one final thing. So let's say that I have f of xk minus f of x star, which is really what we're after, right? We want to know, like, what does the objective value look like at xk? Well, I claim that it is less than or equal to 1 over k times the sum I equals 1 to k of f xi minus f of x star. Why is this? So think about what this is. This is the average error over the previous iterations, and this is the error of the current one, right? But remember that we showed all the way at the beginning of our proof that at every step of our algorithm, the value of f decreases. So every term in this sum is upper bounded by this one. Do you see that? So in essence, I'm saying that, like, well, at worst, I am the average of all the previous errors. I'm typically better than that. Like, this is probably a strict inequality, but like, whatever. Cool? Okay. Well, conveniently for us, we actually have an expression for that right here, right? That is an upper bound. That is exactly the thing that we bounded in our sum. So this thing is less than or equal to x0 minus x star squared over 2kt. So see, the k here comes from the 1 over k here. Yeah, and the rest of this is just the previous inequality. Isn't that cool? This is a neat little proof. So essentially, at the end of the day, if we step back, what did we just show? We showed that if we do gradient descent and our function is Lipschitz, we take a sufficiently small step size, then the values of our function necessarily converge to the minimum value at x star. And it does so at a linear rate, right? You see this 1 over k here. The way that we did that was kind of surprising, actually, is you kind of like bound the sum of all the previous errors, and then you show that like they can't increase or decrease too quickly. Like they increase at a predictable rate. Cool? Any questions about that? What was that? Oh, almost certainly. Did I forget a square? Yeah, you're right. There's a square missing. Where did that go? Oh yeah, there should be a square. That's a good question. Yeah, I guess assuming the rest of our proof is right, there should be a square in the slide. I'll double check that. In my mind, that's a constant factor. But you're right. One way or the other, we just show that it converges. And this is what happens the first time we use the slides for a course. Thank you, Paul. That's a good catch. All right, so you guys are going to remind me when I get back to my office today to double check that. And also, one of the sums is indexed over the wrong thing in the textbook. I noticed while I was writing. Okay, but subject to that, the kind of cool thing that we learned is that we actually didn't need any kind of line search at all. Okay? All right, fantastic. So you're going to use this thing in your homework to show convergence of gradient descent for a very particular choice of f, which is useful. And with that, please study for your midterms. Again, you get a sheet of notes. It is otherwise closed book. It is during this course section. If you have an issue, you have a conflict, an emergency, we will send you to OGC or S-Cubed. So let us know ASAP. If you need accommodations, also let us know. I haven't heard from any of you. And with that, we will see you next time. Good luck. Math is scary. It's hard to write these things live.